Hi everyone, welcome back to the QEC session. In our last talk, we will have Vincent Steffan, and he's going to talk about logical operator and Fold-Transversal gates of bivariate bicycle codes.
Thank you very much. I hope I'm in the right position for the microphone. And yes, the talk is called Logical Operators and Fold-Transversal Gates of Bivariate Bicycle Codes. And I think we had at least 2 talks already which somehow touched similar things as this talk, but I think it will still be quite nice. So I wanted to start by warming up a little bit and by kind of intuitively explaining you what these fold-transversal gates are that we will talk about. And for that, I just want to look at the tori code that we all know. So we have some qubits sitting on the edges of a lattice, and we have the usual tori code stabilizers, and everything lives on a lattice with periodic boundary conditions. And I think everybody here knows that we have 2 logical qubits in the setup, and that we can choose bases of logical operators like this. So we have maybe on the first logical qubits these 2 operators, and on the second logical qubits these 2. And one thing I want to stress here, which we will see later why I'm stressing this, is that one of these pairs only lives on horizontal qubits, so only on qubits that live on horizontal edges, and the other one only on vertical qubits. So they don't interfere with each other, which we will soon see is kind of a nice property. And I want to really just very intuitively explain you what I mean with fold-transversal gate without going into any technical definition. So let's try to implement some logical gate, and let's try to do a very naive thing. Let's just apply Hadamard to all of the physical qubits, and then we will swap along this diagonal. So we just apply swap gates for like the qubits that are mirrored across this diagonal. And I mean, it's not hard to see that this will preserve the code space, because stabilizers will be mapped to stabilizers, and you get actually all stabilizers back. So this will preserve the stabilizer group, and by that it will also preserve the code space. And I mean, once you have realized that, the next question is, what is the logical operation you get from this? And here's where this property becomes very handy, that the logical operators had this nice structure. For example, I mean, if you want to track what does the logical operation do with the first x operator, then you see it will turn the x's into z's, and then it will kind of, instead of having it horizontally, it will make it vertically on the lattice. And if you track this for all of the logical operators, you will see this implements Hadamard on both logical qubits. And this was very easy. And this was very easy because the logical operators are kind of structured. Okay? And so the first part of the talk, I will explain to you why actually this not only works for the tori code, but for every kind of code that has a product structure. And then there's like these hypergraph product codes, which you already saw. And if you take hypergraph product codes of cyclic codes, you get codes with a certain translation invariance. And when you kind of kick out the product structure from these codes, then you get what is called a bivariate bicycle code. And what we also already saw is that bivariate bicycle code, they are kind of attractive because they have much better code parameters than the product versions. But we will see that there it's not so easy to do the exact same thing that we just saw. So to do this concretely, I will first tell you a little bit about classical cyclic codes. Then I will tell you about these quantum codes with product structure. And then I will drop the product structure and will tell you what we can keep and what not. So yeah, I really wanted to tell you 2 slides about cyclic codes. So cyclic codes are extremely easy. So to have a classical cyclic code on n bits, you need n bits. You put them on a circle. And then you need to specify some check. And then all of your checks will just be cyclic translations of this one check. So for this code, this would be the set of checks that you have. This would be a parity check matrix. And we see that all checks are cyclic translations of one single check. And in fact, it turns out the same thing kind of holds for code words. So actually, the space of code words will be spanned by cyclic translations of one single code word. Okay, maybe this is a bit complicated. What does that mean in practice? In practice, it means, for example, here you have h times this vector is 0. So this is a code word. We could say that this is 1, 1, 0, 1, 1, 0. And then this and its cyclic translation will span the code space. And to be prepared for algebraic arguments we will see later, I want to very quickly give you the proof idea of this. And the proof idea is by translating everything to algebra. So we want to translate everything to algebra, and we do that by putting monomials on each of the bits. And it turns out that this ring, where we identify x to the n with 1, has exactly as many monomials as we need, namely n. And when you think about it, once we have done that, every single thing that we talked about so far is a polynomial. For example, our code word here is 1 plus x cubed plus x to the 4. This check here is also a polynomial. And when I told you you need n bits and one check to define a cyclic code, actually you only need this one polynomial. That's all you need. This is what defines your classical cyclic code. And then, I mean, if you calculate it, turns out that this ideal in this polynomial ring, whatever that means, is exactly the code space. And then maybe you know that every polynomial ring in a single variable over a field is a principal ideal domain. So this is exactly the statement that we need. So long story short, somehow if you translate everything into algebra, it becomes very easy to see that this is true. Okay, this is all I wanted to tell you about cyclic codes. And now I want to tell you something about these codes that have a product structure, like toric code does. So these hypergraph product codes, how we call them, they are a systematic way of constructing a CSS code from a pair of classical codes. And they have a very easy recipe of constructing them. So you take two classical codes, you draw the Tanner graphs of them, and then you take the Cartesian product of the two Tanner graphs, and then you have certain rules which vertices will be qubits or x checks or z checks. So I use these rules here. You can use other rules. And also here we have some sort of structural insights on the logical operators now. So first I want to tell you that, like the edges in the graph, they come from the edges of the classical codes. So for example, this z check, the blue one here, will have the following connectivity coming from the connectivity of this bit and of this check. And the code words of these hypergraph product codes, as we also saw in a previous talk, they're kind of easy because they kind of come from code words of the classical codes. So the logical operators of the quantum code, they come from code words of the classical code. In practice, for this code, for example, you have a basis of logical operators, which looks like this. And you see that everything is either only in one column or in one row. And these are exactly things coming from the code words of these two classical codes. And I mean, to be very precise, from their transpose. But and when you look at this, you see that you have the exact same property that I really liked about the toric code. Namely, everything lives either only on horizontal or only on vertical qubits, and somehow things don't interfere with each other. Okay, and because of that, for example, if you would apply the same Fold-Transversal gate to this now, the analysis would be kind of as easy as before. Like, there's really nothing that is more complicated here. You can track the logical action as we did before. Yes, and so now I want to go to the special case of what happens when you have a hypergraph product of two cyclic codes. And I told you that for cyclic codes, basically, for a cyclic code, you only need one polynomial. So for a hypergraph product of two cyclic codes, you will need two polynomials, namely the two polynomials specifying the two codes. And again, this L will be the number of bits of the one classical code, and M be the number of the bits of the other classical code. So what we also saw is that somehow things became easier by labeling the bits of the classical cyclic codes with monomials. And we can do actually the same thing here, and it's quite easy also. But now we need, of course, we have kind of two spatial directions. We have the x direction and the y direction. So we will need like two variables. And actually, we need to kind of label the horizontal qubits, so qubits sitting on horizontal edges by themselves and qubits sitting on vertical edges by themselves. So for example, let's label the horizontal qubits with green monomials and the vertical qubits with yellow monomials. And then for example, if I want to specify a Pauli Z operator, it will just be a tuple of polynomials, right? Because I just have to tell you where is it supported. Right. And then if you think about it now a little bit, or if you like do the calculation, you will see that, for example, x checks, they are just of the form some polynomial times this CD vector, where C and D were the checks of the classical code. So this kind of reflects that the checks of the hypergraph product, they come from the connectivity of the classical code. And so because of that, logical Z operators, they correspond to tuples of polynomials satisfying this algebraic identity. C times F plus G times D must be 0. And yeah, if you attended the QEC tutorial, you know that we can describe CSS codes with these chain complexes, and then the homology of the chain complex will give you the space of logical operators. So this would be the chain complex describing the code. And so this is so what we saw is that for a hypergraph product of cyclic codes, we can span the space of logical operators, of logical Z operators, by logical operators that are only on horizontal or only on vertical qubits. So they are of the form in this language here, f, 0, only on horizontal qubits, or 0, g, only on vertical qubits. And in fact, it's enough to take only 2 of those and all of their translations. Then we get the whole thing. Yes. And now I want to kind of drop the product structure. So this had this nice product structure. Because of that, everything was easy. And we somehow want to drop it. And for doing that, let's think again what we did. So what we did is to define a hypergraph product of cyclic codes. What we took is we took 2 univariate polynomials in this ring. And then we defined the following chain complex. I mean, this is just everything we did on the last slide. And this gives you a CSS code. And I mean, the most obvious way of generalizing this is instead of taking univariate polynomials, you now take a bivariate polynomial, which will give you a bivariate bicycle code. So if you stop assuming that your 2 polynomials are univariate, you kind of drop the product structure. So to see an example, these 2 polynomials, they are not univariate anymore. And if you look at these checks, somehow these checks, they don't have this product structure anymore. And if you look at this, so the ones here familiar with hypergraph product codes will know that you will never get a hypergraph product code with these parameters, because I mean you need at least 144 here instead of 98, 2 times the square of 12. So these it turns out that if you drop the product structure, if you're willing to trade in the product structure, you get much better parameters. This is kind of the game that we are playing here. But of course, when we drop the product structure, everything I told you on the last slides, we cannot apply anymore because everything was kind of relying on that. Yes, what else? And here's like a table just manifesting that they have better parameters than the hypergraph product. There's a couple of parameters for these codes. And we want to kind of now try to rescue as much as we can from the structure of the logical operators that came very naturally in the product case, okay? And one thing that we saw is that the space of logical Z operators was spanned by only by only vertical or only horizontal logical operators. So only supported on horizontal or only on vertical qubits. And algebraically, that meant it's of the form f, 0 or 0, g. And because of that, now for a general bivariate bicycle code, we will define a Z operator to be pure if it's of this form. So if it's only supported on horizontal or only on vertical qubits. And the whole code is pure if we actually can find a basis of the space of logical Z operators that is pure. And then what we also saw is that if we take a hypergraph product of cyclic codes, then the code words of the cyclic codes, they give us the logical operators of the hypergraph product code. And for code words of the cyclic code, we only need one code word, and we need to kind of move it around, and it will give us all code words. So we call a code principal if the same phenomenon holds here. So we only need 2 representatives, and we can move them around, we can translate them around, and we get all of the logical Z operators. And technically, this would be how we define principality, but that's maybe not so important. So stressing it again, hypergraph products of cyclic codes are pure in principle, and the question is, when are general bivariate bicycle codes pure in principle? And I think this is the slide with the main insights from this talk. So this is again the setup. We have our 2 polynomials defining a bivariate bicycle code. We have our 2 definitions, pureness and principality, which is something we had in the hypergraph product case, hypergraph products of cyclic codes. And actually, there's a very algebraic way of checking when a code is pure. Namely, a code is pure if and only if the ideal generated by C intersected with the ideal generated by D is equal to the ideal generated by Z times D. Okay, this might seem very technical, but actually this polynomial ring here turns out to be very nice when L and M are odd numbers. So in fact, when L and M are odd numbers, the code is pure. Like this condition holds. And in fact, when L and M are odd, it's also principal, because this ring this ring here will be a principal ideal domain when L and M are odd. And then maybe to also treat a little bit the even case. So in general, the even case is not really understood. But if L and M are even, then we can say a little bit, and the little bit is that we call a polynomial semi-periodic if it's of this particular form, which a lot of the codes in the table I showed you before actually are. And then it turns out when a code is pure and the polynomials are semi-periodic, then the code is also principal. Okay, that's maybe not so impressive, but what is a little bit cooler is that we have a, in this case, we have a kind of very clear formula of how to construct the logical operators, which I will show you a little bit later. Yeah, we're doing well in time. I can tell you a little bit how to see that. So, okay, so this will be very algebraic, so basically we are interested in logical Z operators. So we're interested in Pauli Z operators that commute with all X stabilizers, but we kind of want to mod out the Z stabilizers themselves, right? Algebraically, this means we are interested in tuples of polynomials f and g, such that Cf is equals to dg, so it commutes with all X checks. And we want to take this modulo B, where B is just the space of all Z-type stabilizers. And then it turns out that there is an exact sequence. Exact sequence means that the image of one map is the kernel of the next map. So it turns out that there's the following exact sequence describing C. So yeah, we can look at this. So this turns out to be an exact sequence. And it already looks pretty much like what we want to look at, because you have kind of this direct sum decomposition into kind of pure things. But what we still need to do is we need to kind of take this exact sequence. We somehow need to have Z modulo B here instead of just Z. And it turns out that you can actually take this quotient. So this is kind of the main workhorse of our paper. So you have this exact sequence, which is a little bit longer. But you can see that now we have here the space of logical Z operators, Z modulo B. And when you look at this, this here is really describing the pure logical operators. So basically, we need this map beta here to be surjective in order for everything to be pure. And if you know about exact sequences, then you know for this to be surjective, this space here needs to be 0. So we have the ideal identity. Okay? And if this was a little bit too quick, that's not a problem, because now we do something fun again. We look at examples. So let's take the examples that we already saw before, namely this code here, this 98.612 code. And of course, it's well chosen because L and M are odd, so the code is pure in principle. And it's also semi-periodic. I told you about this semi-periodicity. So there's a formula for constructing these seed logical operators. And the formula I don't want to explain. I just want to show you a picture of what comes out if you apply this formula. So this is a logical Z operator only living on horizontal edges. And since the code is principal, we only need to take two of these logical operators, and we need to kind of move them around, and then we get a basis of the space of logical Z operators. That would look like this in the picture. So it's very nice. And so we have only on horizontal and only on vertical qubits, and the same for the X-type operators. And then if you now would go and, for example, as a use case, would be interested in what is the action of my fold-transversal gate, if it's applicable, here it's applicable. If you want to kind of track what the action of your fold-transversal gate is, then it's almost as simple as for the toric code, because you have this very nice basis to work with, where things don't interfere and so on and so forth. Yes, and this is really looking at this, I want to remind you of the first two slides. So we saw for the toric code, everything is extremely easy, because we had these well-structured logical operators. And somehow by working very hard, we kind of recovered this, although we kicked out the product structure. So somehow we can still have this. And that's, so I want to quickly wrap up. So again, I told you, toric code has very nice structured logical operators, and because of that, it's kind of easy to understand. For example, we can understand the action of fold-transversal gates. And then I try to convince you that this holds whenever you have a product structure, and that you have a certain principality whenever you have product of two cyclic codes. And then we worked kind of very hard to see how much we can rescue of this when we dropped the product structure. And it turns out we can rescue quite a lot. For example, when the lattice sizes are odd, basically the same story still holds. So yeah, so the takeaway message, so these Bivariate bicycle codes, the ones where you drop the product structure, they have better parameters than the product versions. And they're also, from a mathematical perspective, they're very nice to treat. And I actually only have one open question for you. The open question is, if I give you two polynomials, what can you tell me about the code, else than what I just told you? Like, just looking at the polynomials and their relative position in the polynomial ring, what's going on? And I think that's it. Thank you very much.
Yeah, nice, although not very comprehensible talk. So, okay, so anyway, so you went very quickly at the very end when you said about the fold-transversal transformation on this particular code. Can you sort of go in more detail what transformation is?
What the transformation is?
Yeah, so, well, for toric codes, you have just parallel swap on all the qubits, parallel H on all the qubits.
Yeah.
So what is the transformation on the logical qubits here?
Aha, yeah, so it's described by this block matrix here. So basically you have this block form. This is what you can rescue. Like, it's not as, but also if you think about it, if you do, wait, let's go back. It takes a lot of time, I'm sorry, but if you do it for the hypergraph product codes, okay, it's this slide here. So if you do a fold-transversal gate here, I think you already get some sort of effects where it's not only, for the toric code, if I do this fold-transversal gate, it's just on every logical qubit, it applies a Hadamard. But here I think, I'm not quite sure, but I'm pretty sure that here you already have like some sort of like, logical qubits kind of interfere with each other. Like, it's not only like H, but somehow something is maybe also swapped in the logical qubits. And for the Bivariate bicycle codes, the structure of, wait, I'm sorry. Okay, here's the example, very good. So basically, if you plug in this matrix, and we really did this by hand, if you plug in these logical operators into, for example, this fold-transversal gate, I think you get this matrix out, where T is this matrix here. Does that make sense?
Not really. So can you go over the elements of this matrix just to explain what is going on?
Over the elements?
Yeah, so what does it mean? So you have 6 logical qubits.
Yeah.
Okay, so that's 2 to the 6th dimension.
Yes.
Hilbert space.
Aha.
Is this the unitary matrix? Or
No. This is a 12 by 12 matrix, because we track the action of the logical gate on the 12-dimensional symplectic space, right? So if you 6 Z operators, 6 X operators, and like you have a 12-dimensional space with a symplectic inner product, and this is where the 12 logical operators live, and this is where this matrix lives. So, but I think there should be an easy way. I mean, there is an easy way of translating this into a unitary, but this is not the unitary, I think. Yeah. This is just kind of tracking the action on the logical qubits. Does that make sense?
Well, not really.
I'm sorry.
Can you say some qubits are interchanged, some qubits are being...
Yes, I think so. But I think that here there's 2 ones. It means that there's something interchange or something. I don't know. Okay. Yeah, I don't really. I would need to sit down and calculate it precisely. Yes.
Okay. So this is just some action on the logicals.
This is just some action on the logicals, but it's still kind of nice because it has, for example, this block form. Yeah.
Maybe just following up on Willy's question, is it like a circuit of Hadamard and swaps at the logical level as well?
I don't know. Might be. I don't.
That's where you get the hypergraph product case, I think. So.
Yes, I mean it might be. I'm not. I would need to sit down and write this down, but yeah.
But it's definitely a Clifford gate, I guess.
It's definitely everything we do is Clifford. Yeah.
Yeah. Okay.
Yeah.
Thanks.
I think next to you.
it looks like a tableau to me. Yeah, how like each logical like transforms into each other logical. But that's okay. I had a different question. So, have you ever thought about using this basis of logical operators to reason about the fault-tolerant schedules? For example, the original Bivariate bicycle code paper, they just had, I don't know, 900 different schedules, and then they just numerically picked the one that was optimal, and they saw it empirically that it was distance preserving. But maybe using this kind of like basis of logical operators, you could argue somehow fault tolerance properties of these C0 orderings. I don't know if that.
I don't know.
Okay.
I don't know. I don't see the connection, but
okay.
Maybe, I don't know.
Thank you for the very nice talk. I enjoyed it very much. I just had a few sort of rapid-fire questions about these diagrams. Am I correct that the top left diagram, that's illustrating what the checks look like, right, in the code?
Aha, this one.
Yes.
Yes.
And how can we see the checks in the diagram from the polynomials C and D?
Aha, yeah, okay, so basically C and D, so you would need to label horizontal and vertical qubits with monomials, and you would label all vertices and all faces of the lattice with monomials, and then somehow the support of a check, you need to kind of multiply. For example, there would be in this blue plaquette, there would be a monomial. Then you need to multiply it maybe with C to get the support on the horizontal qubits, and with D to get the support on the vertical qubits. Does that make sense?
Yes. So that's why there's 3 terms on horizontal qubits and 3 terms on vertical qubits, because C and D
exactly,
have 3
exactly.
Okay.
Yeah.
And so in the top right, you have 6 logical operators. You have 6 logical Zs and 6 logical Xs. Am I correct that you could get many, many more with other translations, but they're all equivalent to these ones through the various stabilizers?
I mean, we want, like here, I wanted to write down a basis, yeah.
Right, yes.
But you could choose differently, yes.
And since the distance of the code is 12, there should be a weight 12 logical operator. And these all look like they have much higher weight. Does the weight 12 operator look very ugly, or?
Yeah, so I mean, like the minimal weight logical operator of the code absolutely does not have to be pure. Yeah. So it can, I think for most, I mean, I don't know, but in cases I tried, it usually does not live only on horizontal or only on vertical qubits. So the minimal weight logic, like this is definitely not minimal weight, yes.
Thank you very much.
Yeah.
Nice talk. We know like one of the issues with the bicycle codes is that it's really hard to lower bound the distance of them. So I'm wondering like if your new results, particularly in identifying the structure of the homology group here, can help to provide some better lower bounds on the distance of the codes.
Yeah. So So I think this very much connects to the open question. Like if I give you the polynomials, what can you tell me? And I think, for example, it's easy to see the logical dimension of the code from the 2 polynomials. But it's absolutely not easy to see the minimal distance of the code from the 2 polynomials. And I think it's just a hard question, I would think. I think I have some ideas about certain L and M's, and like sometimes you can say something, but in general it's a very hard question to say something about the distance of the code, because
Okay, thanks.
Maybe you said this, but I missed it. How do you search over which logical operators? Like, say you just said like there's one choice which is not pure and the others are. How do you search for which are the pure ones and which are?
So here it's this thing that the code, like the polynomials are semi-periodic, so we just have a formula for one pure operator, and then we just need to move it around to get all of them. Or we need 2, one on the horizontal and one on the vertical qubits. But basically here there's just a formula that we have for a specific logical operator only supported on horizontal qubits. Yes. Does that make sense?
Sort of.
Yeah, thanks for the nice talk. I had a question about is there any value at looking at the impurity of certain bivariate bicycle codes? There are certain logical operators which may be pure and principal, and then they might have fold-transversal gates, and treating the rest of the code as a subsystem code. Is that a direction that you've investigated in?
No, I have not. But yeah.
Do you think that that's a viable approach based on this framework?
Yeah, I think a code is either pure or it's, yeah. I mean, maybe you talk like, and you could ask how many pure operators out of all. I mean, no. How large is the space of logical operators that are pure compared to all logical operators? But no, I have not thought about this at all.
All right, thank you. And maybe just a quick follow-up. Apart from fold transversality, do you think there's other benefits for pure logical operators?
I think in general it's very good to understand. I think in general for these bivariate bicycle codes where you drop the product structure, how logical understanding anything about logical operators I think can be valuable, just because it's very hard to understand somehow. Yeah.
I guess since you mentioned an open question, what can you tell in general or brief for specific structures whether or not a code has fault-tolerant, syndrome extraction or really good syndrome extraction based on just the code parameters and the code structure?
I have not thought about syndrome extraction for these in this language, no.
And sorry, just pure, like you're using the word pure in a different way than pure code is a non-degenerate code, right? Like the lowest weight stabilizer.
I guess, yeah.
Okay. Lowest weight stabilizer is less than the distance for these codes, right? Yeah.
No, this is completely not related to this.
Thanks.
Yes. Yeah.
Good talk.
So this comes to the end of the sessions. Thanks, Vincent and our speakers again.
Yeah.